Welcome back to Calc 2. This is the last section in 7.3, and today we're going to learn, well, kind of about a whole new set of functions called hyperbolic functions. So to start off, let's kind of take a look at, let's remember our basic graph for a hyperbola. You may or may not remember this. You would have learned it in pre-calc 1. This is a hyperbola that is centered at 0, 0. And it is 1 unit in either direction on the x-axis. So it's a standard equation for a hyperbola. Now, well, this is the standard formula for any hyperbola. We're going to look very specifically at those where the focus is 1 unit. And actually, to really get into hyperbolic functions, we're only going to look at the right-hand side. So we're just looking at this half of our hyperbola. As we go through hyperbolic functions, you are going to find a lot of similarities to your trig functions, which is good in that the identities and the formulas will look very similar. But please understand these are not trig functions at all. When we talk about trig functions, if you recall, everything revolved around a unit circle, and our trig graphs depended upon the angle, remember, and for sine of alpha, we always looked at the y value. For cosine of alpha, we always looked at the x value. And our sine and cosine functions, which were periodic functions, for sine, of course, where these were the x-axis represented the angle, it depended upon what the y value was. So that's why at 0 degrees, the y value is 0. And at 90 degrees, our y value was 1. And the same for the cosine function. We're going to do something similar with our hyperbolics, but we're going to go off of not the unit circle, we're going to go off of this right-hand side of our standard unit hyperbolic graph. But to do that, we're not really looking at angles. Instead, what you're going to look at is the area formed when you go from the origin out to the graph. And very similar to our trig functions, our hyperbolics, which you'll find very quickly is a trig function with an h on the end. So we call this sinh, it's the hyperbolic sine of our angle is still the y, and cosh of our angle is the x. But in this case, it's not really the angle we're looking at, it's actually the area. So let's think about that for a second, and let's focus on our cosh function first. So if we focus on our cosh function, and I'm just going to call it the graph of cosh x just to keep it simplified. And if cosh kind of represents what the x value is, well, if we're flat and we're at 0, that x value is a 1. So at 0, oops, we would be 0, 1. Now, as our angle or our area increases, so does our x value. So it's going to kind of go like this. Now, what if our area is under and it's actually negative? Notice the x values remain the same. So this area is going to have the same exact x value as that area. So it's a very symmetric function. Your cosh hyperbolic function actually looks very much like a parabola, but it doesn't have the relationship of a parabola. That is a hyperbolic cosine function, which we call cosh. Now the sinh function, which is sine, well, for that we have to look at the y values. What's the y values doing as I increase this area? So at 0, my y value is 0. So this one actually has a value at 0, 0. As the area increases, well, the y values will increase. But now look what happens as the area. Notice these are now negative y values. So this function looks a little more like that. Again, very similar to our x cubed function, but it's not. So again, what I've done there is just kind of shown you the relationship of trig functions. You do not need to worry about the area. We are literally doing a slight introduction of hyperbolic functions, and I kind of wanted to show you where these graphs came from. But again, you don't need to worry too much about what I just did. We are touching upon hyperbolic functions. You will, especially if you're an engineering student, you will come across this in a much, much later calculus class. The important piece is, what are these functions? What is cosh x and sinh x? You know, in trig functions, it was very clear it was x and y. Not quite the case here. Believe it or not, our cosh and our sinh functions, our hyperbolic functions, are very closely related to e. And to show you that, I want to go into Desmos, all right, where I am going. Go, move that up a little bit so you can see it. And in Desmos, I'm going to go ahead and go into function, and let's start with cosh. If I scroll down, they're all the way at the bottom. There's our hyperbolic trig functions. And we're going to do cosh of x. Boom. You can see that was the graph I just made. That is your basic graph of cosh. So I said they're very closely related to our exponential function. So let's take a look at how closely related. And, you know, this is something you will need to actually memorize. So hopefully by showing how it evolved on the graph, it'll help you actually memorize. So, all right, to start, I'm just going to do our function. So I'm going to go e to the x. And you're thinking, well, they're not very closely related. I don't really see much of that relationship there. You do start to see, notice how these distances across are very similar. Well, what if I were to widen my e function? And I can actually widen my function by simply dividing by 2. Just in widening that function a little bit. Oh, now we get to see that relationship. Let me see if I can fix this screen a little bit, so hopefully you can see it better. And I'm like, all right, well, I have half of it. How do I get the other half? Well, what if I were to simply turn my function around? So instead of e to the x, think about, well, what makes your function, instead of going, and hopefully you can see my little dot, this way, I want to flip it and make it go this way. Well, then I would need e to the negative x. You see that in green? And once again, widen it by dividing by 2. So e to the x divided by 2 kind of follows the right side of the function. E to the negative x divided by 2 follows the left side of the function. So why don't I just put these together by adding them? And if I go ahead and add e to the negative x divided by 2, you can see right away they're the exact same function. So cosh x is exactly the same as e to the x over 2 plus e to the negative x over 2. That's something you want to write down. That's something you want to memorize. So let me go back to my notes. And our first important piece of information is that cosh x is equal to e, and I'm going to write it this way, or you can have e So that is really important, and it's going to define all the rest of our functions once we get what we call our sinh function. That's our hyperbolic sine. So let's go back to Desmos. Whoops, wrong screen. And I'll X out of that and X out of that and say, okay, let's put sinh on there. There it is. Just sinh of x. And let's start with e to the x. Well, again, not wide enough, so let's go ahead and divide that by 2. So since we've already done the last one, let's think about that for a minute. What do you think? I definitely need the other side, but now I need it not to go this way, right? Not to go like this, but then to also flip down. So I got to basically I have to reflect it over the x-axis and reflect it over the y. So how about this? Instead of plus, let's do minus e now to the negative x divided by 2. And there you go. Same function. So let's go back to our notes. And sinh x equals e to the x minus e to the negative x divided by 2. Or if you like separating them, doesn't matter. You're going to put a nice big red box around this. This you need to know. From here, you can literally just get all of your other functions. So from here, because here's what's nice, and here's what's nice about them being so similar to our trigonometric identities. Because they follow a lot of the same properties, tanh of x, our hyperbolic tan function, is simply going to be sine over cosine. Or sinh over cosh x. Which would then give us, if you do the math, e to the x minus e to the negative x over e to the x plus e to the negative x. The hyperbolic cotangent function is the inverse of tan, so that's e to the x plus e to the negative x, e to the x minus e to the negative x. And you can continue from there. The hyperbolic secant function, of course, is 1 over cosh. So what's nice is there's a lot, you don't have to memorize a lot, but we're going to get into some of the identities, and there are some differences, so don't go. This one's just going to be 2 over, right? Secant is 1 over cosine, so the hyperbolic secant is 1 over the hyperbolic cosine, and that's going to be e over e to the x plus e to the negative x. And of course, the hyperbolic cosecant is 1 over the sinh function, which is 2 over e to the x minus e to the negative x. So we'll put that also all in red. And these are all of your relationships that you do need to know for your hyperbolic functions. But if you know cosh and sinh, you can kind of derive the others from that. So I do expect you to know this part for the test. I expect you to know a couple of the little identities, like these reciprocal identities, and I'll make sure I point out, but for the most part, we are just doing an introduction. Use these notes, use what you learn here to do your lab, to do your math lab. I'm not going to make you memorize everything about hyperbolic functions for the test. When I give you the review for the second test, I'll be very clear on what you really do need to know for the test, because I don't want you to have to memorize, and you're not going to get a formula sheet. But let's go through just stating some of these identities real quick. Oops, let me put that in black. So you can see, yes, there are a lot of similarities, but keep in mind, they are not trig functions. Number one, they are not periodic. You saw it in the graphs. They are not periodic functions like trig functions are periodic, and the identities are going to have slight differences, and we're going to see it right away with our Pythagorean identities. So here are some basic. These will be in the notes that I listed, if you don't want to write them all down, the notes that accompany the video, from the notes from the text, so you'll be able to just pull those notes up and see all these listed. But let's start with our Pythagorean identities. Now, in trig, sine squared plus cosine squared equals 1. This one is slightly different, unfortunately. Cosh squared of x minus sinh squared of x equals 1. And since, again, we are only doing a slight introduction, I'm not going to go through proving any of these identities. You can kind of take a look in detail at the textbook or look online if you want to do that. But, at some point in your math career, some of you may get back to these, in which case you can delve into them a little deeper. We're just giving a little overview. So our next Pythagorean identity is that 1 minus tan h squared equals, oops, I don't know why I wrote that backwards. So do keep in mind tan and secant kind of go together with a lot of things. Cosine and sine go together. So cosh and sinh go together, tanh and sech go together. And our last Pythagorean identity is cotang, hyperbolic cotan. These are very hard to say. Sinh and cosh are kind of common. Tanh, sech, cosech, coch, just call them hyperbolic cotangents. Minus 1 equals the hyperbolic cosecant squared. So there's your Pythagorean identities. There's some cool double angle identities that come into play, such as cosh of 2x is the same as sinh squared x plus cosh squared x. So there's kind of the Pythagorean identity you're accustomed to, sine squared plus cosine squared, but it doesn't equal 1, it equals cosh of the double angle. Here's another one that you might remember from trig, and that's sinh of the double angle. And this one's very similar, is sinh of x, cosh of x. So any of these you might come across when you're doing your work. Let's take a look at a couple more. Our squared angles, so cosh squared x is going to equal to cosh 2x plus 1 divided by 2. And sinh is going to equal to cosh 2x minus 1 over 2. Again, I don't believe in a lot of memorization, so I'm not, I'll let you know exactly what you need on the test, but you're going to need to refer to these while you're working through your lab and while you are working through your trig functions. We also have the sum and difference, so, we have there's your Pythagorean when it relates to the hyperbolics. Here's some double angles. Here's some squared angles. We do have the summation identities, so sinh of x plus y will equal sinh x cosh y plus cosh x sinh y. And cosh of x plus y, here's your other sum. Is going to equal cosh x, cosh y. So just like with the trig functions, the cosine does the x and y together first, or the sinh separates them. The only difference is here you don't have the negative, and this kind of comes up because it's not periodic. Plus sinh x, sinh y. So there's your summations. Some examples of what you will have to do in your homework or on your lab is, proving your identities. And the way we prove any of these, so suppose you were asked to prove that, we'll pick on cosh 2x equals cosh squared x plus. So it's not the identity you need to memorize. I'm going to go back to, what do you really need to know? This. Super, super important you know that relationship. Because you can use that relationship to prove any of these identities that I could give you. And yes, this could be on a test. How do you prove it? Well, just plug it in. Cosh 2x, so what does that mean? Well, this is just saying my angle instead of an x is a 2x. So if I plug it into my formula, for the exponential function, well, instead of an x, I have 2x. I need the right-hand side to look like that. Well, right now, what does the right-hand side look like? It looks like basic cosh with just x squared plus basic sinh, which is e to the x minus e to the negative x over 2. And all you need to do is the algebra. Be able to square. You will end up squaring these numerators a lot, so make sure let's do it off on the side for a second. Something happens every time you square one of them. So let's take a look at what it looks like to square them. So when you square a binomial, remember the basic, it's square the first term. Well, that's just ex times ex, by the way. You add your exponents as e to the 2x. You multiply them together and double. So it ends up being 2. Multiply them together. I'll write it out for a second. And then you square the last one, and that ends up being e to the negative 2x, because e to the negative x times e to the negative x, you add your exponents, negative x and negative x is negative 2x. Well, look at these middle terms. Remember what I just said, you add your exponents, right? Well, what's e to the x times e to the negative x? That's a negative x. It doesn't really look like one. That is a negative x. You add your exponents. Well, x minus x is 0. It ends up being plus 2 e to the 0. So it's just e to the 2x. E to the 0 is 1. So 2 times 1 is 2. So just be careful, because that's kind of what happens every time you square one of these. So now let's bring it back together. And let's square this. This was e to the 2x plus 2 plus e to the negative 2x all over 4, because it is squared. You can kind of follow the same pattern we did in red, but with the negative, it ends up being e to the 2x minus 2, because when you multiply the 2 together and double it, you get minus 2. The e to the x's become e to the 0, which is 1, and that becomes e to the negative 2x over 4. All right, so far not so bad. You have your common denominator, so you can just put everything together. Because you got this nice common denominator, I can just add all this up, and when I do that, well, my 2's cancel, right? So what does that give me when I add it up? E to the 2x plus e to the 2x is 2e to the 2x. E to the negative 2x plus e to the negative 2x is 2e to the negative 2x, all over 4. You can factor out your 2. And that is simply going to equal, cancel the 2 and the 4, e to the 2x plus e to the negative 2x over 2, in which case you can clearly see that your left-hand side equals your right-hand side, in which case it is proved to be true. So that is something you may need to do. Now, but we're in calculus. We're beyond just looking at improving identities. We need our calc of our hyperbolic functions. We need our derivatives and integrals. Again, these are all listed. And follow a lot of the same pattern of the trig function. So this is cosh. Derivative of sine is cosh. And the integral of cosh x dx equals sinh, of course, plus your constant. Here's what's nice. The negatives aren't there. So take a look. D dx of cosh. So here's where the difference occurs from your trig functions. It's just positive. So when you're dealing with regular trig functions, you know the derivative of cosine is negative sine, but dealing with hyperbolics, it's positive. And then the integral of sinh x dx is simply cosh x plus c. And we can continue this. D dx of tanh x. I'm thinking you can take a guess. Yes. Secant hyperbolic secant squared. So the integral of hyperbolic secant, whoops, I got a little ahead of myself, squared dx equals plus c. All right, so let's just finish this off. D dx of hyperbolic cotangent is, here is where we come into negatives. It's not till we get to the cotangent, in this case, the d dx of the hyperbolic cotangent actually comes out to negative the hyperbolic cosecant squared. So if you just take the integral of positive hyperbolic cosecant squared x, it ends up being negative cotan x plus c. All right, just two more. D dx of hyperbolic secant is negative secant h tan x. And of course, the integral of hyperbolic secant times hyperbolic tangent is the negative. And the last one, of course, is hyperbolic cosecant of x, and that's going to be negative hyperbolic cosecant times hyperbolic cotangent. That got a little sloppy, sorry about that. So there's your trig functions, hyperbolic trig functions, derivatives and integrals. A couple little examples, and then we'll be done with this video. Like I said, you can just get those from your notes. So let's suppose I want d dx of x cosh of x squared minus 1. Everything you have done applies. You've got a couple items here. Number one, you can think of that as your f function, that is your g function, product rule. I always say you want to kind of make a plan before you delve into it. First plan is you got to deal with the product rule. And then on top of that, hopefully you see ahead and you see, but wait a minute, when I'm doing this function, not only is it product rule, when I take the derivative, I have a chain rule here. So you've got a chain rule inside a product rule when you're working out this particular problem. All right, so you kind of look at it, develop your plan of action, and let's go ahead and get started. So product rule starts. I'm just going to bring down the x. Now I need the derivative of cosh x squared minus 1. So that's simply going to be the sinh of x squared minus 1 times, right, d dx of x squared minus 1, because you need the chain rule. The chain rule says, so that's going to be multiplied by 2x. Okay? So that's your chain rule inside your product, but now we need to finish the product rule. I need the derivative of x, which is just 1, and then you write the other function down. Cosh x squared minus 1. As always, you need to at least clean up your function a little bit. x times 2x is 2x squared of sinh plus cosh of x squared minus 1. Okay. Let's move on. You can have, let's do d dx of ln of secant of 2x. So this is a natural log of a hyperbolic function. This is not a product rule. It's not ln x times the hyperbolic, the sech of 2x. It is natural log of, not a product rule. And this is why you got to take the time to think about what you're doing. This is a basic chain. That's all that is. Not a product, it's a chain rule. All right, chain rules. So when we're dealing with a natural log, we know it's always 1 over. So start there, right? And the numerator is always d dx of whatever you were taking the natural log of. Okay? All right, so let's work that out. The hyperbolic secant of 2x is in the denominator. All right, so what was the derivative of sech? The derivative is negative hyperbolic secant 2x tan 2x times, it's another chain rule. Look, 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 this is a chain, right? It's another chain. So then I need d dx of 2x, which is simply multiply that whole thing by 2. Well, this isn't bad because you can see that cancels with that. And our final answer looks like what? There's a negative 2 tanh 2x. So some of them are just that easy. All right, let's move on to some integrals, and then we'll be done. Integrate. Sech squared of 6x dx. So you know what sech squared of x is. Just go up to what we did here, the integral. There it is, right? Integral of sech is tan, right? Sech squared is tan. So we come back down. But we have a u sub issue here, all right? And if you want to, you can take your time and say, well, I have to let u equal 6x. du dx is du 6 dx. This is a very simplistic u sub. So I'm not even going to really write the whole thing out. I'm just going to say, okay, I don't have 6 dx. I need 6 dx, right? I don't have that, so I got to put a 1/6 out front. So that's the only difference. And that's what I mean by a simplistic u sub is you just need to add that constant that's not there and put the reciprocal on the outside. So it is tanh of 6x divided by 6, and of course plus c because this is an indefinite integral. All right, let's look at it. Let's scoot down to one that's a little bit. So let's go back for a minute. And the one thing I don't want you to forget is this very important relationship. Okay? Which then, of course, once you understand this, you can form any of these. So where does that come in handy? Let me get back to my screen. So what if you were given an integral and you have done similar ones in Calc 1? you may or may not remember on some labs or something. So here's what's nice. Recognize. You would have to try to do a whole U sub with this, but if not, what you can do is start to recognize that, hey, wait a minute, this e to the x and e to the negative, these are hyperbolic functions. In fact, oh, that's tan. You recognize the minus is part of the sine, hyperbolic, and the plus in the denominator is part of the cosine. The 2's cancel away. So you have sinh over, oh, you have tan. This is just tan x dx. All right. Unfortunately, though, if you go back to your integrals, we cannot just take the integral of tan x. We don't have that right now. But we can do relationships of sinh and cosh. Which is really nice because we know they are derivatives of each other. Remember, when you do u sub and you've got a numerator and denominator that are derivatives, you always want the u to be the denominator. It won't work if the u is the numerator. So du over dx is actually, oh, the integral, the derivative of cosh is sinh. Yeah, so this whole function simply, this integral simply looks like 1 over u du. You know 1 over u du, it's ln of u plus c. You got to put your u back in. Look at that. So much easier than the way we did them in calc. If you start to recognize these exponential functions that are actually hyperbolic functions. I'm going to end this as our little introduction to these new hyperbolic functions, let you practice some of the math lab, and we do have one lab for hyperbolics. Well, you know what? I'm not going to. Let's do, and well, in the lab, so before I end, I just want to show you one type of application that you will do. We talk a lot about parabolic things that look parabolic, like projectile motion follows a parabolic path. Very often, though, things that appear parabolic are actually hyperbolic. So if you think about that Koch graph, it looks like your classic parabola, but it's not. So one application of hyperbolic functions it's this idea of a catenary. When we talk about a catenary, you know, think of if you have two cliffs, right? And you've got this kind of free hanging rope between these two cliffs. If you have a free hanging cable or a free hanging rope, right? Call it a cable. It follows a curved shape that we refer to as a catenary. In fact, if you invert a catenary, often arches that we believe are hyperbolic are actually catenary shaped, in which case they are hyperbolic. They're not parabolic, sorry. Think of the St. Louis arch. The argument there is that is actually a hyperbolic function and not a parabola. So these catenary functions have a very basic general equation. And as you can imagine, they come from the Cauchy function. And the general equation of our catenaries are y equals a Cauchy of x over a, where a is any real number. And if a is less, let's see, if a is greater than 0, then we have the look of the free hanging rope, right? Cable. But if a is less than 0, we actually have an inverted catenary, and think of an arch. So you see catenaries in a classic example is actually a telephone wire. When you're going down, a telephone wire has these catenary functions. The a value will be given to you as part of the equation. So we're not going to do an example. I'm going to leave one in the lab for you to kind of look at. Keep in mind, you know, you'll be given the function, you'll be given the a value, and you'll have to do some different things with it. So for example, if you needed to find the length of the catenary, you're talking about your arc length function. So you might have to go back to things you learned in chapter 6 if you're talking about the length of a cable. Then you're simply doing that arc length formula. So don't forget something like that. So that's just something you'll come across in the lab. You might come across in the math lab homework for a simple application. Okay, so that will conclude our intro to these new hyperbolic functions.